not a line. In fact, when we always write down x, y, like this on the plane, on the flat sheet of paper, right? The x-axis represented the x variable. The y was the y. If we're going to now add an additional variable, we're going to need another dimension, aren't we? We're going to need a z-axis. And so it's the axis that actually comes out of the page like this at us. This is the z-axis. Okay? So if I'm trying to just find a point that lives here, like if I'm trying to find the point 2, 2, 2, very simple. X, y, z. The way I would do it is just like you normally do. You go out 2 on x. You go up 2 on y. So you're here, right? But then you have to come out of the page by whatever this distance is, come out right here. That point, right, sitting right there. Three-dimensional space is the point 2, 2, 2. Understand? That's 2, 2, 2. But we can't, I mean, how would you ever take a test and show me what 2.2 looked like, right? You couldn't. So we need to try and find a way of representing three-dimensional space on two-dimensional flat sheet of paper, which is not easy to do. But do you understand that all of these answers that make this true are all points that live in three-dimensional space? Now, is it a line in three-dimensional space? I don't know. I'm not going to tell you that yet. But let's first try and get our heads around how we could possibly draw three-dimensional space on a flat sheet of paper. Let's just try and do it. Here's the way I recommend you do it, all right? There's usually two standard protocols. Draw a line like this, okay? And then what you're going to do is you're going to draw an X, all right? When I say X, everyone thinks this, right? But I want you to squash this X down and make it more like this. So take it and smash it, all right? Watch. Do you see my smashed X like that?
It just popped out of the board.
Do you see it?
I see it.
Okay. I kind of missed it, though, here.
No, that's good.
I'll move it. You might want to draw the X first, then. It's easier to come through with this line afterward. Does everyone see the three-dimensional space now? Okay, now let me show you what happens if you try and do this with this type of X and not squash down. It's a disaster. Watch. This. Does that look like three-dimensional space to you? I'm not quite sure why that one doesn't work as well, but this one always seems to work really well. All right? You can see a little bit here? Yeah.
It'd be hard to see. Like at a higher angle, too.
Now, we have to determine, remember over here, this was our situation here. Okay, so I'm going to put X plus here, Y plus here, to let you know which is the positive direction of the axes. Right? X positive numbers are this way, Y positive is this way. Z positive is coming out at you, okay? Where's Z negative? Going into the board, to the other side of the wall, right? Yes?
Yeah.
Okay, so we need that same convention here. So watch the way I'm going to label this. I'm going to label this X positive. Where's Y positive then? Here?
No, to the right.
This? That's Y positive right there. Yes. So imagine, yeah, imagine this. Here's our X positive and Y positive, right? Imagine that Z-axis coming out at us. If I were to take it and I were to put it like this, okay? You're looking at it like that. Can you kind of see that?
Okay, so
that picture? So it's almost like if I leave this on the desk, it's almost as if I'm standing over here looking at it, kind of like this, from here.
I just wonder why you wouldn't have that, what you have Y plus with Z, you know, and then.
This is the standard way to do it, okay? We always put it's always the XY plane, the flat sheet of paper, is laid down, and the Z is coming up. That's the standard. Now, when I said that Z is coming up, that means this is the Z positive direction, like this. Okay, y'all see it? It's very difficult to graph things with this, all right? So let's try and plot 2, 2, 2, all right? So first, can everyone agree with me that going out 2 on the x-axis would be something like 1, 2. There's 2 on the x-axis. And then 2 on the y-axis would be something like 1, 2. Is that all right with you? So where is it on my picture?
Go 2 up on Z, and then you.
I'll get the z in a second. Just like on the flat sheet of paper, when I was trying to find
It's going to be like
2, 2, that's here, right? I'm just trying to find that over there.
It's going to be like a dime. Kind of like
Is it here?
no.
Here?
Yes.
It's in there. Do y'all see it's in there?
Yeah.
So here's how I get to it. If I'm trying to, I know that I have to come out this far. I just need to come out here somewhere, right? And put a dot.
Do parallel.
I run parallel to the y-axis, and then I run it down until I hit that point right there, okay? Which is here. Now imagine just a real light line I'm going to draw right there. Well, that came out a little bit heavier than I wanted, okay? And then what I'm going to do, yeah, I could do it the other way also. I could run parallel to the x and come up, but instead what I'll do is I'll just measure, that's 2, right? That's 2. I'm going to come over here, I'm going to measure 2 here. I'm going to put my dot right there. See that?
The soft line was there to show it coming into the third dimension.
What's the what line? No, I haven't done the 3 dimension yet. All I've done right now is this. Everyone is looking at this point that's on a flat sheet of paper on the ground. Does everyone see that that point's on the ground?
Yeah.
Now I need the z. So I need to come up 2, right?
Yeah.
So to come up 2, let me first see what's 2 going to be. 1, 2, there's 2. I'm going to measure that. And from this point, parallel to the z-axis, which is just straight up, I'm just going to go straight up right there. I'm going to draw that point right there. Straight up.
Should you always show this?
No, I'm only showing that to help you see it. I hope that helps.
It does.
You go to the right 2 on the x-axis, 2 on the y-axis, 2 on the z-axis. It's sitting there, it's suspended in 3-dimensional space. Okay? Now watch, check this out. You want to see something cool? I mean, I don't know if you'll think this is cool. Watch. Here's the point 0, 0, 0. Right? What is this point right there? Give me the coordinates of that point. This one is 0, 0, 0. This one is what? 2, 0, 0. Everyone see that? Out 2, don't go anywhere on y or z. What is this point? 2, 2, 0. Right? What is this point? 0, 2, 0. Right? You'll see all those? Now check this out. Here we go. Watch. This is only because I have experience with this, okay? But I'm going to go from this point. I'm going to draw parallel to my y-axis. I'm going to draw like this until I get to this point, which is directly above this. And then I'm going to come straight over to 2, and then I'm going to go back, and then I'm going to go like that. Do y'all see the cube? Do y'all see the 2 by 2 by 2 cube? It's a little off. I don't really like that. This one should probably come down a little bit like this. This one should come over like that. That's a little bit better. Still. That's a 3-dimensional box, right?
You gotta find the area.
That's Cal 2 and 3. But instead of this being, and not area, we find volume because it's 3-dimensional. But instead of this being flat up here, we would have like, imagine it's like a blanket, you know, like in the wind, like waving, and then like freeze it. So this is like a surface up here. Okay. What I'm wanting you to see right now is that if you have a linear equation in 3 variables, you actually have to live in 3-dimensional space to understand what the answers look like. So what does all of the answers to this look like over here? That's the question, and I wouldn't expect for you to know, but I heard line, right? If I draw a line in three-dimensional space, every one of those points on the line, so this is a line in three-dimensional space. It's hard to tell where it is, but there's a line, right? Each of these points has an x, y, z. Maybe all the solutions to this equation live on that line. Maybe. But it turns out that's not the case. It turns out that when you have an equation in three variables like that, a linear equation in three variables, then sorry, thought I was doing something else. Then all the solutions to that equation live on a plane, a flat sheet of paper. So imagine, again, in three-dimensional space, a piece of paper lying out in space, but this is an infinite sheet of paper. It goes in this direction forever, in that direction forever, in that direction. But it's sitting there in three-dimensional space. So we live in three-dimensional space, right? So it's easier if I just come over to the corner of the room. I call that corner down there the origin, 0, 0, 0. And I call that way the x-axis. X is down along the wall right here. I call this the y-axis, and then z is this one right here. Then the solution to that equation is a sheet of paper sitting somewhere in this three-dimensional space. This sheet extending out, punching through that wall, punching through the floor, coming this way. It goes infinitely in each direction. It's an infinite plane. And that plane could be, tilted in different directions. Depends on the equation. Understand? So, if I give you three equations, a system of three equations, each of them having x, y, and z in it. I'm just making shit up here, okay? 5z minus equals 2. So there's three equations, right? Three linear equations in three variables, x, y, and z. Then what do our solutions represent geometrically? The intersection of three planes. How many different ways could that happen? Because you told me for lines, what could happen? When we were back in two-dimensional space, two lines either hit each other at one point, didn't hit each other at all, or they were the same line. But if I give you three planes, what's possible? So let me suggest one option. Is this a plane, this wall? Is this a plane, this wall? Is the roof a plane? Where do those three planes come together? At that single point right there, right? So it is possible to have one point intersect? Okay. How about this wall is one plane, this wall is one plane, and a third plane that comes in like this. Then where do they hit each other? In a line, don't they? And that's an infinite number of points. How about if I have this plane, and this plane, and that plane? Then everything on that plane, that would be like the parallel situation. So we have different possibilities, just like we did with the lines. How about one plane is this floor, one plane is the roof, and one plane is the floor in the room below us? 1, 2, 3.
No solution.
No solution. So again, we just have more possibilities with three equations, three unknowns. So what we'll do next class is we'll get into using Gaussian elimination to try and solve this system of three equations and three unknowns. All right? Sound like fun?
So you'll just have to do it twice.
You won't have to visualize it. Look, I don't think I've ever shown a college algebra class how to draw in 3D before, because usually that's not something that you see this early, but I think it's a good exercise. It's not beyond the grasp of you to see that, visualize that. Yes? Not that one. Yeah, I'd have to come up with something for you if it's a bonus. Look, I do need to add one more thing. I know you want to get out of here as much as I do. but this is very important. Everyone's used to seeing this, right? That's a standard two-dimensional sheet of paper. If I come in here with another two-dimensional sheet of paper, whoa, and I draw it like this, is that okay for me to do?
Yes.
Yes. Why?
It's just,
You just proved it, it's to infinity.
I just turned it? That's all I did?
The view of-
Yeah, I just changed the view of it, okay? And I can do that, again, showing you this. This is the standard piece, right? Looking at that. That one, right, is this sheet of paper like this, flipped over. So now x is positive this way, and y is positive this way. So it's just taking that sheet of paper and just flipping it and turning it, right? And it's the same thing. Turns out that for the xy plane, you can label it however you want. It does not matter. And you can always turn it and flip it to make it the same thing. All right? For two-dimensional space, you can do it. For three-dimensional space, you cannot. So when you draw three-dimensional space like this, x, y, z, plus, 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 if someone else comes in here and does y, x, z, there's no way to turn this or twist this to make one of them look like the other. There's no way. And because of that, how many of you have to take physics? Anyone have to take physics? Okay, because of that, we have to agree upon the way we're all going to do it. Because if I do it this way and you do it that way, the mathematics is going to be different. So we all agree on what's called the right-hand rule. The right-hand rule. The right-hand rule says that you take your right hand, okay? And what you do is you point your fingers out the x-axis in the positive direction. Okay, so let me go back here. This is the origin. That was the x-axis, right? That direction. My fingers are pointing out that way. If I curl my fingers on my right hand, they should point towards the positive z-axis, which is over here. And my thumb should point where the positive z is. So fingers down the x-axis, curl to the y-axis, thumb pointing up the z-axis, all in the positive directions. Do y'all see that on this picture, that this is okay?
Yes.
So my fingers are pointing out the x-axis on my right hand. Curling towards, I curl into the y, right? And my z is up. Is that happening here? No, because if I point my fingers down the x-axis and I curl, I'm not curling towards the y, am I? So I have to flip my hand over and curl towards the y this way. But then my thumb should be pointing down the z positive, but it's not. So this is not drawn using the right-hand rule. Yeah? I'll never forget a test I took in a class called Non-Euclidean Geometry, where I did some problem, and I went up to the teacher at the end, and I was like, I'm having trouble with this. You know, I'm using the right-hand rule and all this stuff. And she looked at me, she's like, that's your left hand. I was like, oh, shit. Because I'm left-handed. I was using my left hand for the right-hand rule. And that's all I want to say. Because I showed you how to draw a three-dimensional space, I felt inclined that I had to tell you the proper way to draw it. This is the proper way to draw it. Okay, adios. Have a good Thanksgiving.
I just wanted
See you next week.
to talk to you about this.